Evaluate the expressions in A through F using the graphs of y equals f of x and y equals g of x. So we're given this g of x graph and this f of x graph, and we're asked to answer these questions. So with these questions, this is the operation of composition, g of f of -1, and we're just going to follow the symbols to find the answer for these. So for part A, it says g of f of -1. We're going to start with the inside. It says find f of -1. So on my graph, I want to go to where x is equal to -1, go up to the graph of f, and find the y value, which is 2. So f of -1 is 2. So I've replaced this f of -1 with a 2. So now I want to find g of 2. So I'm going to go to where x is 2, go up to the graph of g, and go over to get the y value, and that y value is 4. So g of 2 is 4. And then completing the problem, g of f of -1, that is equal to 4. Okay, let's try the next one. I have f of 0. So we're going to start on the inside, f of 0. Starting with an x value of 0, I'm going to go up to the graph of f, and my y value is a 1 there. I'm going to change f of 0 to be 1. Now I'm going to find f of 1. I'm going to go to where x is 1, go to the graph of f. I'm already at the graph of f, and the y value is 0 there. So f of 0 is 0. Let's try the next one. F of g of -1. So we'll start with g of -1. We have an x value of -1. I'm going to go all the way up to the graph of g, and the y value is 5. So g of -1 is 5. Now I want to find f of 5. Here's where x is 5. I'm going up to the graph of f, and the y value there is 2. So f of g of -1 is 2. Let's try the next one. G of 4. So we'll start with g of 4. Let's go to an x value of 4. Let's go up to the graph of g, over to that y value, and we get a y value of 4. G of 4 is 4. Now we want to find g of 4, which we just found. So having an x value of 4 going up to the graph of g gives us a y value of 4. Let's try the next one. The next one is, I'll write it up here. F of g of f of 0. So we're going to start off with f of 0. So I want to start with an x value of 0, go up to the graph, go up to the graph of f, and that gets me to a y value of 1. So f of 0 is 1. And I'll carry down the symbols on the rest of this. Now I want to find g of 1. So x value of 1 go up to the graph of g, and I get a y value of 6. G of 1 is 6. Carry down those symbols. Now I want to find f of 6. Let's find f of 6. Here's an x value of 6. Go to the graph of f, and the y value there is 3. So f of g of f of 0 is 3. All right, and we have our last one. G of f of g of 4. So starting with g of 4, we want to start off at an x value of 4, go up to the graph of g. That gives me a y value of 4. So g of 4 is 4. Now I want to find f of 4. I have an x value of 4, go up to the graph of f, and I get a y value of 1. So f of 4 is 1. So now I have g of 1. Let's find g of 1. An x value of 1, go up to the graph of g, and I get a y value of 6. So g of 1 is 6.
On this question, it says, is the function one-to-one? Use the horizontal line test. Okay, so I've added in this definition of what a one-to-one function is. A function f is one-to-one if for any values a not equal to b in the domain of f, f of a is not equal to f of b. So this is saying that if we have x values that are different, then our y values will be different. And so this is a test that we use to basically show if the y's are unique. Now the horizontal line test is how we decide whether that whether that graph is a one-to-one function. And the reason why we use a horizontal line is because if we think about the graph of a horizontal line, and we think about the ordered pairs that are on that horizontal line, all of the ordered pairs will have the y being the same. And so we want the y's to be different. The horizontal line has all the y's being the same. So it's a good comparison to our graph. The horizontal line is the opposite of what we're looking for. So on this graph, we're going to draw horizontal lines, and we're going to pay attention to the intersection points. And since these horizontal lines are intersecting the graph in only one point, we know that there's only one y value. Those y values are not repeating. All the y values are different. Now, it may be a little bit confusing if we focus in on this part of the graph, because it looks like the graph turns into, it looks like the graph turns into a horizontal line as we get closer and closer here, but this portion of the graph never turns into a horizontal line. There's always going to be a little bit of a gap in between this line and the x-axis. Even though we can't see it, if we were able to zoom into this, there would always be a little separation between the line and our graph. And so what's happening to the graph is it gets closer and closer. It never reaches it. So when we do the horizontal line test here, we're only crossing in one place. So in this particular example, this function is a one-to-one function. I've zoomed this way too big. Sorry about that, guys. So this function is one-to-one.
Write an equation for the inverse function and then state the domain and range of f and f inverse. In this question, we have the function f of x equals x cubed plus 4. The first thing I want to do is find the inverse function, which we call f inverse. So to find that inverse function, I'm going to change f of x to y. And then I'll switch the x and the y. And I'm switching the x and the y because that is what inverse functions mean. The x and the y are switched in these type of equations. So that's basically by definition because we're looking for an inverse function. And then I'm going to solve for y in this new equation. So I want to isolate the y. So to isolate the y, I'll subtract 4 on both sides. And I need to get rid of that cube, and the opposite of cubing is cube rooting. So I'm going to cube root the left and cube root the right. The cube root and the cube cancel each other out, giving me y. And then on the left, I have my inverse function, cube root of x minus 4. So we can label that as f inverse. F inverse is the cube root of x minus 4. The next thing that we want to do is find the domain and range of f and f inverse. Now we have some strategies for finding the domain of different types of functions. So I'm going to find the domain of each of these f and f inverse first. So if I look at f of x, that is x cubed plus 4. This type of function is called a polynomial function. And with polynomial functions, there are no restrictions on the domain, meaning that no matter what real number we substitute in, we are going to have a defined y value. And so because of that, we can say that the domain of f is all real numbers, negative infinity to infinity. We'll do the same thing for f inverse. We just found that f inverse is the cube root of x minus 4. As I look at this function, I would categorize this as a root function. We call it a root function because of the radical. Now with root functions, you want to pay attention to the index. This has an index of 3. And the reason why you want to pay attention to the index is because root functions with an even index have restrictions on the domain, but root functions with an odd index have no restrictions. So we have an index that is odd, so there will be no restrictions on the domain of this function. The domain of f inverse is also all real numbers are negative infinity to infinity.
Now we also want to find the range of f and f inverse. Now we don't have as many strategies for finding the range like we did the domain. But if you'll remember, what we did earlier is we switched the x and the y. So what we know about inverses is that the x and the y switch. Domain are the x's, range are the y's. So if we switch the x and the y, the domain and range also get switched. So what that means is that I can use the domain of f inverse as the range of f. And I can use the domain of f as the range of f inverse. So we now know that the range of f is all real numbers, negative infinity to infinity, and the range of f inverse is all real numbers, negative infinity to infinity. So for this question, we are given a quadratic function in vertex form. This is the function here, f of x equals 1/3 x minus 3 squared plus 3. And we want to address the following. We want to sketch the graph and find the domain and range. So this quadratic function is in vertex form, or sometimes called standard form. And what that means is that our function follows this particular pattern. A times x minus h squared plus k, where hk, the ordered pair hk, is the vertex of the graph of the parabola. So looking at our example, you can see the h and k being 3 and 3. So we have the vertex of the parabola. This provides information on how we're going to draw that parabola, where that vertex is. So with a parabola, you either have an up-facing parabola or a down-facing parabola when your quadratic is a function. And the vertex is at these turning points here. So we're going to use the value of a, which in our example is 1/3, to determine which one. Whenever a is greater than 0, we have an up-facing parabola. And when a is less than 0, we have a down-facing parabola. So our a is 1/3, and because that is greater than 0 or positive, we know that our parabola opens up. So we have a pretty good idea of how to sketch the graph at this point. I'm going to draw where the vertex is, 3, 3, which will be here, and we know it's facing up. However, we don't know how wide or thin the parabola is going to be, and that is also determined by the value of a. When a is equal to 1, that is our base function, and if we think about what that graph looks like, we have 0, 0, 1 squared is 1, negative 1 squared is 1, and so you can see that that point is 1 over and 1 up, 1 over and 1 up away from the vertex. But when a is equal to 1/3, that point will be, instead of 1 away, 1 up, it'll be 1/3 up. Now, we have some restrictions here because you guys are doing this problem in my math lab, and my math lab restricts you to clicking only on the points where you have a grid point. So because the y is 1/3, for that point, because the transformation moves that point to a third, you're not going to be able to click that point to draw the graph. So you have to find a point that is matching the grid that you have. So it has to be a whole number in order to draw the graph using MyMathLab's tools. So what you need is a second point on the graph that happens to be using integers. So I would suggest looking for maybe an x-intercept or a y-intercept. In this example, a y-intercept works. So if you find the y-intercept, you're going to let x equal 0. And for your function, that's f of 0. And you have 1/3 times 0 minus 3 squared plus 3. So we'll follow order of operations inside of the parentheses. 0 minus 3 is -3. -3 squared is 9. 1/3 of 9 is 3. And you have 3 plus 3 is 6. So this gives you a second ordered pair on the graph, 0, 6. And because those are both integers, MyMathLab will accept that second click. And you can see how wide the parabola is from there. This question also asks to find the domain and range. The domain is the x values, and the domain of every quadratic function is all real numbers, -infinity to infinity. And the range, we're going to use this vertex. That is the first y value in the range, and all the y values going up from there are included in the range. So our range starts at 3 and goes to infinity. 3 is included because the vertex is included in the graph of the parabola.
In this example, we're going to be given a quadratic function in vertex form. Sometimes it's called standard form. And we want to find the following. We want to find the vertex, the orientation, axis of symmetry, intercepts, and then graph this quadratic function. The vertex form, let me write that down for you. The vertex form of a quadratic is f of x equals a times x minus h squared plus k. And the ordered pair hk is the vertex of the quadratic, vertex of the parabola. So our function is written in that vertex form. So after the minus sign, we can see that we have a 4. That's going to be our x-coordinate of the vertex. And then right here we have -4, that's the k. And that's the y-coordinate of our vertex. So we have a vertex that is 4, -4. The next thing we want to do is find the orientation. And the orientation of a quadratic function is either up or down. The value of a will determine whether that quadratic is up or down. Whenever a is greater than 0, the graph opens up, and whenever a is less than 0, it opens down. In this example, the value of a is 1. We don't see a coefficient in front of the parentheses, so we assume the value to be 1. So a is equal to 1, which is positive or greater than 0, so this parabola opens up. Then we want to find the axis of symmetry. When you have the graph of a quadratic, it's a parabola. And if you draw a vertical line that passes through the vertex, you're going to see that the graph is a mirror image around that vertex. So we call that line the axis of symmetry. that vertical line. So it's a vertical line that passes through the vertex. So for this example, we're going to use the x-coordinate of the vertex, and the vertical line x equals 4 is the axis of symmetry. Next, we want to find the intercepts. I'm going to start by finding the y-intercept. You can find a y-intercept by letting x equal 0. So that's calculating f of 0. That would be 0 minus 4 squared minus 4. 0 minus 4 is negative 4. And negative 4 squared is 16. 16 minus 4 is 12. So we have a y-intercept at the point 0, 12. And I'm going to find the x-intercept. An x-intercept can be found by letting y equal 0. Our equation is in function notation, so rather than having a y in the equation, we have f of x. So we're going to set f of x equals 0. When I do that, I have the equation 0 equals x minus 4 squared minus 4. And I'm going to solve this equation using the square root method. I'm going to isolate this square and everything that that square is attached to. So I'm going to add 4 to both sides to isolate that square. Once I isolate the square, I'm going to square root both sides to get rid of the square. The square root and the square are opposite operations and they cancel each other out. But whenever I square root a square, I gain this plus or minus symbol on the other side of the equation. And square root of 4 is 2. I'm going to add 4 to both sides, and that gives me x equals 4 plus and minus 2. 4 plus 2 is 6. 4 minus 2 is 2. So we have x-intercepts at the ordered pair 6, 0 and 2, 0. Now that I have the intercepts, I'm going to graph this quadratic function. I'm going to use the information that I've gathered. I've got the vertex being 4, negative 4. I have a y-intercept at 0, 12. I have two x-intercepts at 6, 0 and 2, 0. So 4, negative 4, my vertex. I have a y-intercept at 0, 12, an x-intercept at 6, 0, and a y-intercept at 2, 0. When I draw this, I want to keep in mind that these are not random points. The vertex is a very specific point that indicates where the function turns around. We call it a turning point. So this will dip at that vertex and turn around. We also want to keep in mind the symmetry of the parabola. So we should see a mirror image on either side of the vertex. So this gives me the graph of the quadratic equation x minus 4 squared minus 4. Thank you for checking out my videos. Have a great day.